Of course, Vladimir Voevodsky, my collaboration with Vladimir, and this topic in general, A1 homotopy theory, is one of the huge part of my mathematical life, so I'm very happy to be here, and I want to thank the organizer for the invitation. The first time I came here was in 2000, I think, because he invited me, and I came since then several times here, and it's a very strange feeling to know that he cannot come anymore. I have a very good remembering the period in 2000, 2001. Vladimir was at the Instit, but his office was not yet in the main building. His office was in the homotopy house. And it was a very small house around the forest there. And I remember once talking with Vladimir in his office and seeing through the window Pierre Deling walking with his dog and going through the window of Vladimir and giving him the notes of the lectures. And Vladimir told me after, smiling, saying, it's a deal. Pierre Deling takes the notes, and I have to write the notes. So it was a very efficient time. Okay, so it was very nice. So I want to give a survey. So I will be maybe not so precise, but I want also to give some historical details about why homotopy, A1 homotopy theory came in and how I get involved with Vladimir, just a little bit. So the genesis part. So why to look for A1 homotopy theory? So a general reason, why to even wonder about that? At that period, in the 90s, and even before, people were looking for motives, motivic complex, motivic homology, things like that. So why not to look for motivic homotopy theory? Okay, so people were I think it is one of the natural reasons. Motives, motivic homology. So, why not? Motivic homotopy theory. In fact, sometimes this A1 homotopy theory is called motivic homotopy theory. I'm not a fan of this. I usually use A1 homotopy theory, but whatever. So this is a general idea, but personally, in that period, it was in the 95, I was writing my Affiliation, okay? And I wanted to be able to do the following. So it was very concrete. So personally, define a natural. So of course, one can have several ways of thinking about natural homotopy theory. Means homotopy category, model, whatever, everything included, where the following is true. If X is nice enough, smooth, over a field K, for instance, then the homotopy class is from X to Z across the classifying space of the infinite linear group. In that homotopy theory, so H of K, the same K here, should be the K0, the Grothendieck K group of X, of vector bundles over X. Okay. This theorem in classical topology is, of course, well known, and so this was my objective, to be able to define this. I had the feeling it's possible. So for such schemes, this functor is A1 invariant. K0 of A1 cross X is K0 of X. So there is no obstruction, okay? And it was possible. It was possible. So this was my aim. Now, so chronology. So in the spring, so it's just something I didn't explain to many people. There was a conference in Paris. Jussieu. I think it was for the 60th birthday of Max Karoubi, where Voevodsky, so Vladimir, gave a talk on DM. Of K. So of course I heard about this construction, but it was the first time I saw it. And after the talk of Vladimir, I came to him and asked him directly, oh, did you ever think about defining a homotopy theory in the same spirit? And his answer was not very surprising. He said, of course, it's possible. There are some problems, but of course. So, of course, after this answer, I decided that I had to hurry up in finishing my habitation, my work, and send it to Vladimir, which is what I did. So, in the summer, I really finished this work. In this time, I was not very fond of internet and so on, so it was a paper version. I think it was not yet in LaTeX. Maybe it was the beginning of LaTeX, I don't know. So I finished my paper version, and I submitted my habitation. But I didn't send it to Vladimir right away. And in fact, so it's another little sad story. I gave this first version to Bob Thomason, who was my colleague in my office, in fact. Unfortunately, Bob Thomason died this summer, and I never had any comment. And I think, I'm pretty convinced that if he would have given any comment, he would have told me that I'm using Nisnevich topology, because I didn't know about that. I just defined the relation using these squares, which are related to Nisnevich. Unfortunately, I didn't have this. So nevertheless, I decided my habitation was okay, going through, so I decided to send this preprint to Vladimir. So I sent this in, I don't know, in August maybe, 95. I sent my preprint to Vladimir. Per post, paper version, okay, no email. So nothing happened until end of September. So nothing happened. At the end of September, I got an email from Vladimir Voevodsky in his style. Hi, are you the guy who sent me this preprint with the title, Best Vladimir? Okay? So email. So of course I answered the same way, so yes, I am. Best. Nothing happened for the next 2 weeks again, so no email, yeah. But then after 2 weeks, I got an email from Vladimir with, unfortunately I don't have this email anymore, 8 attachments in PDF file with A1 homotopy, stable A1 homotopy, still one operation, blah, 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 blah. Of course, no first draft of proof of the Miller conjectures. You would not send this. So of course I was very surprised and enthusiastic, and we started at this period to communicate through emails. So it was in the fall, 95. We communicated through email. It was kind of fun because we were discovering something, for instance. So it was not clear all the time. Small discussion. If you take P1 smash P1 and you switch the two factors, it was one of the critical points, so we had a lot of discussion. What is the homotopy class of this? Because what is this as a morphism from P1 smash P1 to itself? So what is this? The problem is through complex embedding or the theory of motive, this is the identity. Because P1 has dimension 2, so it's just, but it cannot be the identity because if you have a real embedding, it is -1. So the element was, for sure, it defined over Z, cannot be the identity. Okay, so it was not clear. So it was called epsilon at this time, something like that. And what was discovered after all, so this is, I proved this some time after. This is the Grothendieck-Witt ring of quadratic forms over K. Well, symmetric, non-degenerate bilinear form in any characteristic. And this element, in fact, is a class of the quadratic form -1. Okay, so, but it was really funny to discover this kind of, there were a lot of problems. We also discussed, for instance, related to the construction of Susslin homology of motives and serial operations. Is it possible to understand the symmetric powers of smooth schemes? I think I also have some discussion with Mark after all. It was not clear. In topology, you can find expression of symmetric power of the syllable complex as a homotopic limit. And we agreed that, so there was a lot of discussion and it was very interesting. So of course, at the beginning of the 96, I think it was at one of the Great Lake conference, Voevodsky announced the proof of the Milnor conjecture. I think it's this, so I don't remember exactly when, March maybe, or February, maybe Rick knows. March, okay. March 96, Vladimir announced the proof. Of Milnor's conjecture. So we were still discussing, and I invited him in Paris in the spring, so maybe in May. He visited Paris. I was very proud because I was at the École Polytechnique at this time, which is a bit far from Paris, and I think it was one of the only time Serre went to a talk at the École Polytechnique, so because it was not so easy to let him move that far away. Well, I can explain something, but this was not my point. So it was the first time I really met Vladimir personally. He was spending 1 week and so on, so we had really time together. And once, so we were having some, I don't know, coffee or something like that, or tea. And he put on the table a preprint with title A1 homotopy theory, and he told me, okay, I agree, we should write together. So of course, it was for me a great honor, and I was very happy, and so it was the beginning of a new period. I have to say honestly that this is for me probably the best mathematical award I ever had, okay? So because there are official ones, but this one that Vladimir recognized that we were defining the same thing and was very nice. So we started around this period to write, so which is another thing to do, writing the paper, joint paper. The people who wrote with Vladimir know that, for instance, when he writes some part, it's very hard to make him change anything. Okay, even if you try to convince him. So, and I think the paper was published maybe in 1998 or I don't remember, 9. It took some time, but it was the starting of another period. So with closer contact. So I went several times to Princeton here. He came to Paris, and I started to meet his family. So Nadia, his daughters, Tali and then Dina. So it was a very nice period. I will maybe say something more on that on Friday at the dinner conference. So now I'm going to talk about, well, how we came to the definition of A1 homotopy theory in more concrete terms, and what are the properties that we really wanted. So as I mentioned, one of my aim was this representability of K0, of K-theory. And this is one of the theorem which is in the joint paper, which comes at the very end. But in fact, in this paper, so in the preprint, A1 in theory of schemes, which was general because we work on a general base as long as possible. It was not particular the field. We could not prove anything very special to field, any computation. So except general formalism, functoriality, and so on, there were basically two theorems. The first one, which is the formula that if you take a smooth variety and you add a base point here, it's a pointed space in some way. You take the n suspension and you take this space here, whatever it means. It's also a pointed space, and the morphism in the pointed homotopy category is isomorphic to Quillen K-theory, okay, for any x smooth. But this came at the very end. In fact, the most important theorem was what is called now the purity theorem, homotopy purity, A1 homotopy purity. It is named after the same property in et al. Cohomology. Okay, and so what does it mean? So it's very important, and in fact, it is the essential property of this A1 homotopy theory. It is a direct connection between geometry, algebraic or differential geometry, and homotopy theory. So what is it about? I will draw something. So if Y is a closed subscheme of a scheme X, both are smooth over K, so closed immersion, smooth scheme over K. Let's draw it. So imagine for a while it's a differential topology. So you draw Y inside X, and this is X, and this is Y. So in topology, what you can do is to draw a tubular neighborhood here, and which means an open neighborhood of Y, the small one, which is diffeomorph or isomorphic to the normal bundle. So this is the normal bundle of the closed immersion here. So the point is, in topology, you can draw this. And once you draw this, then you see the map from X to, so first X modulo the complement of that neighborhood. And in topology, this is called the Tom space of the normal bundle. In other way, it is also the total space of nu I with compactified. If you assume that Y is compact, this is a one-point compactification of the normal bundle over Y. Okay? So you see directly the map from X to this Tom space here. If you use this for X being a sphere, it's exactly the Pontryagin construction. Okay? So, and this is a very important construction, and we define this A1 homotopy theory to have the same map here, which is, of course, not obtained by using this. So this is where the Nisnevich topology enters the game. So the homotopy purity theorem, there exists a cofibration sequence. Canonical one. We talk about being equal or equivalent or canonically, so it's canonical. It means if I tell you there is one which is canonical, we'll find it. There is no cofibration of the form, so you take the complement, open complement, X minus Y. It's an open subset or scheme in X. And if you take the cofiber, this is a Tom space of the normal bundle over Y. Okay? In this A1 homotopy theory. So the proof of this, of course, doesn't use any drawing, so you have to replace this, and you have to use calculus of fraction. So you have to put something here called deformation of the normal bundle divided by some open subset, and which map to both of these guy here. And using the axiom of the construction of A1 invariance and Nisnevich topology, you can check that locally this is in fact A1 homotopy equivalence explicit, and globally you can use the topology to prove it is a weak equivalence. So there is a canonical zigzag of weak equivalence in the A1 homotopy sense. Okay, but it's canonical. Okay, it's quite canonical. The easiest example of this theorem is the following. I will not give more details. If you take x smooth over k, and small x being a rational point. Okay, so it's not true that there is an open subset around x which is isomorphic to an open subset of AM, okay, where n is the dimension. But what is true, so x is not locally in any topology, in the Zariski topology, But it is true in the Nisnevich topology. In the Nisnevich topology, so this is where the choice of topology is very important, and this is the reason why we choose this. The quotient x modulo this closed point, the rational point here, is isomorphic as a sheaf, in fact. It's not A1, it's isomorphic. So here I do not write. I usually do not write equal, even if things are isomorphic. So I'm very careful, not because of your talk. It's really isomorphic to AN over K modulo AN minus 0, which is the Thom space of the normal bundle here. Okay? So this was a reason to choose this. And the other reason is also that the representability of K theory doesn't work so easily with the étale topology, because you get étale and so on, so it's not so. So Nisnevich topology is very natural for these two things, okay? So, but mostly for this one, yeah, that you have this. I mean, this construction is a main construction which is used in topology, for instance, for the cobordism theory. Come to this. So some remarks. Sorry. This construction implies, for instance, S duality in the sense of Spanier-Whitehead. Smooth projective varieties. Over K, in the precise sense, in fact, of Attia duality. So very short. So as you might observe, I basically speak about unstable homotopy theory. But in that case, to state this S duality, the Spanier-Whitehead duality for such a smooth variety, X, it says the following. So this is a triangulated category with a symmetric modular structure, and the dual of the suspension spectrum of X plus is the Thom space of the normal bundle of X, with a shift. So the minus D times the Tate complex, the Tate sphere, okay? So the Thom space of the normal bundle of X minus D times, treated by minus D times the motive of P1. This kind of construction implies, for instance, transfers. if you have finite étale, even for y and x being fields, finite field extension, using this kind of duality theorem, you get a transfer in the stable homotopy category, which go the other way. It's a consequence of this. Another one is the fundamental class of a smooth variety, which is used by Vladimir. There is a map from a high smash product of P1 by itself and the suspension spectrum of the pointed P1 to the Thom space of the normal bundle of X, of some model of the normal bundle. So this was defined by Vladimir and in fact explicitly used in the proof of the Bloch-Kato conjecture. So this construction is used at some point. Of course, in topology, we know it's also related to so Thom contributing to cobordism. In fact, Vladimir also used the cobordism. So I just wanted to insist that this property is really important and justify this definition. Just of the homotopy category. So second, yeah, so what Vladimir did also, just before talking about cobordism, the Motivic and MacLean spaces. Okay, you define these spaces explicitly, which are almost so like the infinite symmetric product in terms of schemes of Pn is a product I equals 0, or depending 1 to n of k zi to I. So using this inspiration here, which is an analog of Thom theorem, okay, which say that symmetric product in topology of explicit CW complex are related to the homology. It's giving a model for the homology of the motive. So Vladimir defined this explicitly and was able to compute, or to give enough information on the motive with Z model coefficients of these, with the mod L version. Element in dm of k. Okay, so once you have this space has a motive, and you can take out the mod L motive here, you can take the mod L here, and this computation, in fact, is the analog of the computation by Cartan and Serre at the beginning of the 20th century. And this is really what Vladimir did. And if you look at the published version of his paper on student operation and so on, he compute using the unstable computation. Okay, this is the usual way you do it unstably. You compute the homology of all of this, and then you get the stably the student algebra. Okay. Third, cobordism. MGL, so he also used this spectrum. So again, it's a stable object, which is built as any spectrum with the list of all the Thom spaces of all the universal bundle of rank n over BGLN. Okay, you take BGLN, there is a natural, whatever the model you take, there is a rank n universal vector bundle. You can take its normal, its Thom space, and you can put all of this into a list which defines the Thom spectrum. Okay, and combining, so this is an important object that Voevodsky used formally. He basically didn't know almost nothing, just a few compatibility with topology, but he had to use this object, and combining this object here the Tom space and the previous construction, which I unfortunately erased, the fundamental class in the proof of the Milnor and Bloch-Kato conjecture. This was one of the synod operation, and this construction was really a completely new idea of Vladimir. But what about this? So together with, so this is the homotopical version of cobordism, and with Mark, we inspired by, with Mark Levin, inspired by the paper of Quillen, which always, I was always fascinated by this paper by Quillen, which is a paper on complex cobordism. If you read the introduction, Quillen thanks the visiting of 1 year at the IHES and the influence of Grothendieck's theory of motives to write this paper. So I was always fascinated, and with Mark, at some point, we could turn this around in the other way, back to Motivic or A1-algebraic theory. We defined, using the same idea, a geometric cobordism version, which, because it is completely geometric, should only be compatible with the, so we define this and prove something on that, which was only aimed at mimicking that part of the cobordism. So it is graded and it is bigraded, so you have to take this diagonal here, 2 times n, and Mark proved in fact that, well, with some assumption of Biggs field, that these are the same. Which means exactly the same theorem as Tom, okay? So just to mention all of this to convince yourself that this construction of A1 category just works. I mean, everything which is reasonable and provable is true, and you can do it. And it's compatible with everything you know. And using this, for instance, so not using this, we don't need that. It was proven a bit later, I think. But with the computation we did here, we could prove also a formula related to the Bloch-Kato conjecture, which is called the general Rost degree formula, which I mentioned here because, in fact, we had this idea because this formula is just a reformulation in this setting of the analog of the theorem of Quillen. This was the theorem of Quillen. If you rewrite it here, it's exactly the degree formula. So I write it here. Well, more or less. It's really the analog. General form. So this was proven together with Mark Levin as a consequence. In fact, I remember that we were basically done with everything. Everything was done. And by the way, said, oh, by the way, we can prove this. So something like that, I think. Yeah? It was not the aim, it's just a consequence of computation. You just read through the paper of Quillen and you get this. So what does it say? So if you take a projective morphism, between smooth projective varieties, both of them, but F is not smooth, it's just automatically projective. Then you have the following formula in the cobordism ring of the point. So any smooth projective variety has a class in the cobordism ring of the base point by pushing forward. Okay. So in that ring, which is also, we proved it isomorphic to the Lazar ring, which is a topological one, mu star. Okay. Then the class of y, okay, so this one here, minus the degree of f. I will explain what is the degree of f. It's an element here also. It's just the generic fiber of f. So I'm in characteristic 0, say. So everything is generically smooth. So if you take a generic fiber, it's a smooth projective variety. It could be empty, in which case you get 0 here. If not, it's a class here. And it is defined the cobordism ring of the function field, but the cobordism ring is independent. What we prove, it's L, okay? So time x, so this is not, of course, 0, but this lies in some ideal depending on x, which is generated by the cobordism class in the Lazar ring of resolution of all closed integral subscheme of x of strict positive codimension. So you take a prime cycle in x, different from x. You take a resolution of this, birational resolution here, and you take its class in the cobordism ring. Okay? So it's just say that the cobordism ring of y in some sense, the consequence, is generated by the identity plus these classes as a module over the Lazar ring. So if you write this, it's exactly this, and you push forward everything on the base point. And this had some consequence related to the work of Rost and Vladimir on norm varieties. But it's also true. So let me mention something which is more unstable, which I did. So I'm going back to unstable A1 homotopy theory. And these were mathematics related directly, more or less, to Voevodsky, to Vladimir's proof of Milnor and Bloch-Kato conjecture. All these extensions, of course, there is a lot. I do not mention the stable stuff. There were also new stuff stably. But these were related to Vladimir. So something which I did later on is the unstable version of the first theorem I put on the blackboard here, and which is also true. So for any affine, so it's very important here, smooth K-scheme, X, so K is a field, homotopy classes of in this A1 homotopy category of X to B, G, L, R. So GL of R is a group scheme. It's a space. You can define this classifying space. So this is also a space. It has a A1 homotopy type. You can compute this in the A1 homotopy category. Then this is exactly the set isomorphic. So again, something here. Canonically, naturally, in bidirection with a set of isomorphism classes of rank R vector bundles. Over X. So first, why affine? Because if X is not affine, it's wrong in general, because then that functor on the right here is not A1 invariant. There are a vector bundle from 2 over P1 cross A1. It's easy with the matrix and the intersection of the two open subsets. Which are not induced from P1. Okay? If you take the 1 section and the 0 section, they are not isomorphic. So it's wrong in general for projective schemes. But for affine, this functor is A1 invariant. It's a theorem due to Lindell, which is a generalization of theorem by Quillen and Suslin on the so-called Serre problem. Of course, it's non-trivial. It's non-trivial, but if you look through, for instance, if you have to teach it, the classical theorem in topology, it's also non-trivial to prove that homotopy class of map from CW complex to BGLR of C, for instance, is the same. You have to work. You have to glue together. You have to. So it's not completely formal, but it's true here as well. I will not mention this further, but there are a lot of consequences of this, very concrete. So one. Deduce various obstruction. For instance, to split a trivial bundle of rank 1. In a locally free module over the ring of the scheme here, which is affine. A vector bundle is the same thing as a locally free or finite type module over the ring of X. So now this theory tells you you can understand topologically what is the obstruction to split off a rank 1 trivial factor of this. You just have to look at the fibration here, GLR minus 1 to BGLR. This is a morphism. The homotopy classes of map of X to this one and this one are isomorphic classes of vector bundle, rank 1, R minus 1 and R, and you have to study the fiber. And the fiber here is homotopy equivalent to AR minus the 0 section here. And one knows enough on this space. For instance, it is R minus 1, R minus 2 connected in this setting. So you can get that if the dimension of X is less than R minus 2, you can always split this, which is a well-known fact which was proven by Serre completely algebraically. But then, if X has dimension, for instance, R, you see exactly one obstruction, okay, which is called the Euler class. It's a cohomology group, and there is a class in the cohomology group of X of dimension R in the first non-trivial sheaf here, okay? So the same theory, you can open the Minor-Stachev book, for instance, and you do the same thing, okay? So there is a lot of new, and in fact you can go further, okay? Even if the dimension of X is bigger, there are people, some Azok, Fazel and co, who can do this. So there is quite a list of classical analogs, so let me now move to more open problems. So this is the beyond part, okay? So here are some examples. So as I mentioned before, Vladimir used the homotopy cobordism spectrum, and with Mark we connected this directly to algebraic geometry of smooth projective varieties, or to proper morphisms to between smooth proper varieties. There should be various analogs. Cobordism. Well, I was born in classical algebraic topology, so I know a huge list of classical problems which I can try to put in this world here. So this is the reason why here, okay? So, for instance, orthogonal. So in topology, if you want to think about an orthogonal structure of a real bundle, real vector bundle, it's basically nothing, because any vector bundle has an orthogonal structure, because ON is a compact form of GLN. Okay? So you can always put a metric. So this is basically nothing. It's the usual, the simplest cobordism theory, and this is the one René Thom solved and computed at the beginning. Okay? But here it's not trivial. So nobody knows for the moment, because so this spectrum here and orthogonal structure on vector bundle are non-trivial. It's related to quadratic form. So, and for instance, so the Motivic version. So I don't know how to the geometric MO. For instance, in topology, it was one of the main theorem of Thom at the beginning. This spectrum split as a wedge of mod 2 length spectra shifted. And this is wrong here. So nobody knows what it is. So nobody has a clue on what could that be and what would be the geometric interpretation. There should be a definition, like we did with Mark, of morphism, or projective morphism, from smooth scheme to a given X with an orthogonal structure on the relative normal bundle of the morphism. that should be interesting. So I remember discussing once with Marcus Ross on this, and he was convinced that this, the understanding of this spectrum should be very closely related to the Minor conjectures, module 2, because it contains quadratic forms and probably also Motivic module 2 unleveling spectrum somewhere. So you have also oriented cobordism. So oriented, I will not insist much, but you have several definitions of being oriented, which do not look exactly the same, but I was convinced that the cobordism theory should be the same. Anyway, you can say first an oriented manifold is a manifold such that the tangent bundle has an SL structure, lifting, okay? So the determinant is trivialized, can be trivialized. There is a weaker notion, which is used very often, which say that the top extra power of the tangent bundle is a square. So to give an orientation means to give a square root of this bundle, okay? And for instance, Pn for n odd at this property, okay? So not every smooth proper variety has this property, and there should be a very interesting cobordism theory to remember. In the classical topology, the oriented cobordism ring was the last to be computed entirely because it was fine, a lot of torsion, so it should be also this way here. And this is also one of my favorites here, although I didn't convince so far so many people, the parallelized cobordism. I think I already talked about this with several people in this room. So which means a smooth proper variety, smooth projective variety with trivialization of the normal bundle, of a stable choice of the normal bundle, if it exists somewhere. And this should be related, like in topology, and it was the Pontryagin construction at the beginning, should be related to a stable homotopy group of spheres. So of the sphere spectrum in this A1 homotopy, stable homotopy category, which I put with a double bar to make it very important, okay, which is a Motivic sphere spectrum. Spectrum here. I will not take too much time, but very often, so what it means, any element of these groups here, the stable homotopy group of the sphere spectrum, should be interpreted in terms of class of parallelized variety, somehow, okay? And yeah, of course it's not trivial, but I think it is reasonable. Let me finish by giving you other directions. I have to choose. So let me, yeah. Second, this is also something which I try to advertise because I was born, well, in that surgery theory. So what is the meaning of surgery theory? I will not explain what is exactly to do a surgery on a smooth differential manifold. It is related to the picture I draw. I mean, this open tubular open neighborhood and so on, so you can modify the boundary and so on. But in classical topology, it says the following. Smooth projective varieties over K, of course, over a field is very special, so I have no idea in general. Should be understood in pure homotopical, so A1 homotopical term. Okay, so I will give some comments because probably many people here start to be very nervous about this. For instance, this theory will not tell you many things on abelian varieties, of course, because abelian varieties are discrete in this world. So they are equal to their own pi zero. So the problem of abelian varieties, they do not really belong here because it's like a discrete set. What can you do for surgery on that? But it should be incorporated in that picture anyway, but it will not prove or say something more. That theory should be more interesting for A1 connected varieties. So some comments, so smooth projective varieties, X, so either the pi zero is non-trivial, okay, like an abelian varieties, for instance, these kind of things, okay? And then you can try to say, okay, let us fiber this over the pi zero and consider each fiber as kind of a smooth proper or another type of smooth proper and do this for any connected. But either you are this, or if the pi zero is trivial, then the pi 1 is non-trivial. So there is a new phenomenon here in algebraic geometry. I mean in the A1 sense. I do not mean in étal, okay? Because I see some heads starting to, I mean in the A1 sense, okay? If a smooth projective variety is connected, A1 connected, then the pi 1 is non-trivial. Because any element of the Picard group, any non-trivial GM bundle, give a non-trivial morphism of pi 1 to GM. Okay, so you can prove these facts here, which make this theory, if it exists, very complicated, because in topology, the people started with John Miller, for instance, to understand this phenomena by considering highly connected, compact, differentiable manifold. You could say let X be a compact differentiable manifold of dimension n, which is of dimension 2n, which is n minus 1 connected, for instance. And you could summarize everything coming from what happens in the middle. Here it's not possible, because if you assume it is connected, then pi 1 is non-trivial. So you have to deal right away with a non-trivial pi 1, which means with S-cobordism, Motivic S-cobordism or whatever, okay? With Arvind Asok, we wrote a paper in that direction for surfaces. Some evidences for smooth for some time. So smooth A1 connected means for surfaces rational, okay, over an algebraically closed field for surfaces. In the case of smooth rational surfaces over algebraically closed field, you can do something which has this flavor, okay, because you can say what are the such varieties, and you can see cobordism between them and when there is a cobordism. So you can see that this is not completely crazy. So basically, just to finish here, and maybe I will finish at this point here, well, although I wanted to say something more. So what are this homotopy description, just for the people who have no idea on what is surgery theory? It's quite amazing. I basically already talked about this direction here. So if you take X a smooth projective variety here, you can assign to this the homotopy type of X. So you forget completely X is a smooth variety, you just take the homotopy type up to this isomorphism in the homotopy category. Then you take its A1 chain complex, or some variant, which is like the motive. It's a bit more, but plus the duality. It's a chain complex which has a Poincaré duality inside. But then you have to care because it's even more complicated because it's duality with presence of the pi1. With pi1, so it's a bit more complicated. I told you it's almost never simply connected. It's an object, algebraic, like a motive with a duality, with a Twitz's coefficient for module over the pi1. But it's kind of linear, plus the pi1. And you have the fundamental class. So this pi1 smash n defined by Vladimir. So these are three data which are completely homotopy invariant. You don't care about exactly what it is. You look at these homotopy classes here. This is a chain complex up to quasi-isomorphism with duality and so on. And what is amazing in topology, so the same situation tells you if you have this CW complex finite, such that the chain complex has duality, reasonable, and this fundamental class, there is an obstruction, which is Hirzebor signature formula, which combine the Chern classes. So the Chern classes, maybe I forgot to put the, well, maybe I should put also the map to BGLN, the classifying space of the normal bundle, which gives the Chern classes of the normal bundle here. So using the Chern classes here, using the duality, you have the signature. So you have an obstruction. There is a formula which should be true. And what is amazing is that if this formula is true, then this data come from a compact differentiable manifold. And there should be the same phenomena. So for surface, rational surface, it works in this way somehow. So there is some positive, but of course it's a big stuff. So let me finish with another one. I cannot resist because of the presence of some people here. So two general facts. It's going to be very quick. If you take X smooth, general, it's a usual problem in topology. You can complete it. Completion makes life theoretically easier because you have spectral sequence which converges. Usually in topology you complete at P, at a prime. Let us do the Motivic completion. So which means, for those who knows, is the Bousfield-Kahn completion using the adjunction between the homotopy category and the DM category. Okay, so this object here is somehow the universal object you can build from X by mapping to something which can build from motives and Alma-MacLane by taking iterated fiber and so on. Okay? HZ, okay. Thanks. You don't like mu. In the old preprint here, there are some old preprint of Voevodsky. Sometimes you use mu. H mu Z was the Motivic. So this is the Motivic completion. Strangely, very often, this is an equivalence, a weak equivalence. It's not something which is almost, it's an equivalence, homotopy equivalence. I don't have time to explain, but very often, the pi1 is nilpotent, the action is nilpotent, it's an equivalence. There is no obstruction, okay? But it's open, okay? But this is connected, for instance, to the rigidity theorem of Sustin and Voevodsky. If a variety at this property here, that this is an equivalence here, then it satisfies rigidity. Because this is a homotopy inverse limit of things which are built from motives, for which this is true. So if you have this, okay, then X satisfies the rigidity problem. Okay. Of course, I got to this problem using BGL, for instance, or BG for a smooth algebraic group related to the Friedlander-Miller conjecture, but I will not talk about this right now. And now, let me finish now. I told you I cannot resist. So here's also conjecture. I was born in this. My advisor proved the general Sullivan conjecture. So GM is an analog in the setting of Z mod 2. Okay? So if you have a smooth variety on which GM acts, you can take the invariant subscheme. It's a smooth variety as well. So you can, so either you already know that they are equal to the completion, but if they are not, you can complete and ask whether this is the homotopy fixed point of GM acting on the completion. So I guess there should be some assumption, okay, I don't claim I have a general fact, on X for which this should be true, okay? And in fact, moreover, from what I say here, you could also remove the hats in general, which give a formula expressing the homotopy type of the homotopy fixed point by an explicit homotopy inverse limit. So thank you very much. I'm finished.